Hi guys, welcome back to my channel. Today we're going to have a quick look at Pascal's triangle, and we're going to see how we use Pascal's triangle to help us to determine the probability of different events. So just as a quick intro to Pascal's triangle, the way that it works is that we start off with the number 1. And what we're going to do is we're going to pretend that the rest of these values on this row are filled with zeros. And we're going to take these two numbers and we're going to add them together and form this number here below. So 0 and 1 make 1, and then 1 and 0 make 1. Then we're going to repeat this pattern so that we have 0 and 1 make 1, 1 and 1 make 2, and 1 and 0 make 1. Then we just continue to repeat this pattern until we build this triangle, and this triangle here is called Pascal's triangle. There are a lot of different uses for Pascal's triangle, but one of the ones that we've used previously is for binomial expansion. Binomial meaning that we've got two different factors inside the brackets that we're going to be expanding. We can see here that if we raise x and y to the power of 0, then the value of that function is equal to 1, and so the value of our coefficient is also equal to 1. If we were to raise x plus y to the power of 1, then the coefficients of 1 and 1 are now going to start to form the basis of Pascal's triangle. And you can see that as we increase the power for each one of these functions with x and y, that when we add the like terms, we're continuing to see this pattern build. So when we're doing binomial expansion, we've used Pascal's triangle, but we can also use it for binomial probability. Here's a really simple example. Say that we had a coin and we were recording the number of outcomes. Now, just to make it simpler, why don't I refer to just the number of heads? So say for this example here, the number of heads would be equal to 1, and here the number of heads would be equal to 0. So if we were to toss the coin once, the possibility of getting heads once would be 1, and the possibility of getting tails once would also be 1. So we can see this is again starting to form the basis of Pascal's triangle. If we were to toss this coin twice instead, the possibility of getting 2 heads is equal to 1. The possibility of getting only 1 head, we've got 2 different ways that we can do that, so n is equal to 2. Or if we had the possibility of getting no heads, so that is 2 tails, that would be 1 possible outcome out of the 4. If we were to continue to increase the coin tosses, we can see how this is going to continue to follow Pascal's triangle. I'm going to show you an example now where I would be looking for the probability of getting a certain number of heads out of a certain number of tosses. So binomial probability, as we've kind of alluded to before, is when we have 2 possible outcomes. It's right there in the name, binomial. So let's say that we are looking for exactly x number of successes. So here we're going to define x as our number of successes, and n is our total number of trials. Say for example, we were looking at the probability of getting 3 heads when we toss a coin 5 times. In this case, n is equal to 5 and x is equal to 3. There are a couple of different ways that we can represent this. The first way is very simple, so just using a pair of brackets, we use 5 for the number of trials and 3 for the number of successes. Another way that we can do this, and there's a couple of different variations in the notation. Sometimes I see it written as NCX, and sometimes I see it written as NCR. There's also some variability in how they actually position the n's and the x's here. So sometimes I've seen it written as NCX like this, or NCR like this as well. So it's all different notation that means the same thing. So let's have a go. Let's draw up our table, and this is going to be quite a big table. I've zoomed out a little bit here so that you can see everything that's going on. But what I've done is I've created a tree diagram which outlines all of the different possible outcomes of tossing a coin 5 times. And I've highlighted the ones where I've gotten 3 heads in particular. Now, each of these has an equal chance of occurring. So all I'm going to do is just going to count up the outcomes. And here I can see that I've got a total of 10 out of 32 outcomes. Now, If we were to deal with anything that would be more complex with this, and this is already starting to get a little bit crazy, then we would need to come up with a bit of a smarter way to figure out how to find this probability. So what we can do instead is we can actually use Pascal's triangle to help us to do this. Here we have Pascal's triangle. So what we're going to do, as we go down each of these rows, this is going to be related to our number of total trials. So here, this is when n is equal to 0. Here, n is equal to 1, n is equal to 2, n is equal to 3, and so on. Oh, that was a bit of a dodgy 3. There we go. All right, as we go across here, this is our number of successful outcomes. So we're going to call this our number of successes. So here we would have 0 successes, 1 success, 2 successes, 3 successes, and so on and so forth. So in particular, what we're doing is we are looking for, we had 5 trials, and we are looking for 3 successes or 3 heads. So we're going to go down. This is 0, 1, 2, 3, 4, 5. So we're going to go down to this row here. And then we're going to go across 0, 1, 2, 3. So using Pascal's triangle, we can see that there are 10 different ways or 10 different pathways in our tree diagram that are going to give us 3 heads out of 5 coin tosses. So let's use this information now to calculate the actual probability. So if we have 10 different ways, 10 different pathways that we can get 3 heads, we're going to find the probability of getting a head and a head and a head. So that would be 1/2 to the power of 3. So that would be a head and a head and a head, multiplied by the probability of getting 2 tails, because obviously if we have 3 heads out of 5 tosses, the other 2 options must have been tails. So the probability of getting a tail and a tail is going to be equal to 1/2 squared. And when I put this into my calculator, I actually get 5 out of 16. And 5 out of 16 is just a simplified fraction of 10 out of 32. So we do indeed end up getting the same value. So what would this look like if the probabilities weren't equally likely? Here we have a similar problem, but this time my coin is not a fair coin. So I toss an unfair coin 5 times. The chance of getting a head is 0.7, so I've weighted the coin on one side. What is the probability of me getting 3 heads now? So we're still going to use the same process as before. So we're looking for the possibility of getting 5 total trials with 3 successes. And we're going to count along 0, 1, 2, 3, 4, 5. Then we're going to count along 0, 1, 2, 3. So again, this is going to be equal to 10 successes, or 10 different pathways if we're going to draw a tree diagram. So there's 10 different pathways or 10 different ways of getting 3 heads, multiplied by my probability of success. So that's going to be 0.7 to the power of 3. And again, this is going to be the probability of a head and a head and a head, multiplied by my failure to the power of 2. So this is going to be the probability of a tail and a tail. And this time when I put this in my calculator, I get a value of 0.3087 or 30.87%. Now, there is a way that we can do this on our calculator. Sorry, this was me just comparing from before. So as we can see, there is a slight difference in those probabilities. But there is a way that we can do this on our calculator. And it varies depending on the calculator that you have. But for most scientific calculators, there's a little yellow button and it does literally just look like NCR like this. So when you go to type it in your calculator, you would literally just type in 5, then press that button, a little C will come up, and then 3, and then it will give you that outcome of 10. So there you go. That's how we can use Pascal's triangle to determine probability in situations where we have 2 outcomes in an experiment. All right, guys, I'll see you in the next one.